Good day, everyone. Welcome to the mathematical dissection of a water ripple. In this video, we'll break down the ripple equation step by step, starting from the equation itself and uncovering the hidden details that make waves so beautiful. So grab a pen and paper, and let's dive into the mathematics of ripples and waves. In part 1, we'll build a visual understanding of what derivatives and partial derivatives represent. This will set the stage for a deeper dive into the ripple equation. Complex equations can be a bit tricky, but here's a neat trick. Freeze a few variables and treat them as constants. This simplifies the math, making it much easier to understand the equation step by step, and we'll demonstrate it in just a second. Notice that we've now frozen time at 86 seconds. Next, we'll see how this step of keeping time constant helps simplify the wave equation. So let's break down our wave. A is the amplitude, basically how tall the ripples are. Alpha is the damping factor. It shows how quickly the waves fade away. Omega is the oscillation rate, how fast the wave wiggles. K is the wave number, telling us how close the ripples are packed together. And since all these factors are constants for a given wave, we can treat them as fixed, which lets us simplify the wave equation to its essentials. Now let's substitute these constant values into our equation and see how it simplifies. And there's yet another trick we can use. Let's set y equals to 0. You'll notice in a moment how this reveals an even simpler form of the equation. Notice that we now end up with an equation that depends only on x. This simplified form will be especially useful for our next step, where we'll visually explore what a derivative means in mathematics. Now, if we plot the graph of this simplified equation, we get the following curve. We've overlaid it on the 3D plot of the ripple equation to show that it represents a special case, a subset of the ripple equation, where time is fixed at 86 seconds and y is fixed at 0. Next, let's take a moment to visually explore what the derivative of a function actually represents in mathematics. At first glance, this definition might look a bit intimidating, but its meaning is actually quite simple when we look at it from a geometric perspective. For example, if we take a look at our simplified ripple equation, the derivative can be found by comparing how much the curve's height changes between 2 points when one moves along x-axis. And this can be done by taking the ratio of the vertical change in height to the horizontal distance between them. And this ratio is nothing but the slope of the green line between the 2 points. Now observe that at point x, the curve's height is given by z of x. And at x plus delta x, the curve's height is z of x plus delta x. Next, let's denote the difference in heights as delta z. Thus, the ratio in the derivative equation comes down to the following, which in turn is nothing but delta z over delta x. Now, let's see what happens as delta x gets smaller and smaller. Keep an eye on the slope of the green line. On the plot, you'll notice that the ratio of delta z over delta x is closing in on a specific value. And that limit, the value this ratio approaches as delta x shrinks toward 0, is what we define as the derivative of the function at x. In mathematical terms, this ratio is called the derivative of the function at x. Geometrically, it represents the slope of the curve at that point. Now that we've covered what a derivative of a function is, let's return to our original ripple curve. Previously, we set y equals to 0 for our demonstration. But clearly, y isn't limited to 0. It can take any value. So what happens if y equals 1, or y equals minus 1, or any other number? This is where partial derivatives come in. A partial derivative lets us focus on how a function changes with respect to one variable at a time, while keeping the others constant. In our ripple example, we can keep y fixed, just like we did in our simplified curve. Geometrically, you can think of it like slicing the 3D surface of the wave at different values of y and looking at the curve along those slices. And now, when we take the derivative of above given equation, where both y and t have been set to constant values, the resulting derivative is called a partial derivative of z with respect to x, denoted by dabba z by dabba x. Next, if we keep x and t fixed, the equations we get are slices for different values of x. And now, if we take the derivative of this equation, the derivative will be called the partial derivative of z with respect to y, denoted by dabba z by dabba y. Thus, partial derivatives are a very handy technique to dissect or slice a multivariable equation in one direction at a time. So partial derivatives are essentially a natural extension of the derivative concept, from one-dimensional curves to multidimensional surfaces. So here's a question to end part 1. If we lock x and y and take the partial derivative with respect to time, what does that reveal about our ripple? Stick around for part 2, where we'll break it down and uncover even more hidden details in water ripples. And that brings us to the end of this video. If you enjoyed it or found it useful, don't forget to like, share, and subscribe. Drop your thoughts in the comments. I'd love to hear them. Until next time, take care and see you in the next video.